In this lecture, we're going to go over really quickly another few examples of operators, specifically the identity and projection operators. We're going to start with the identity operator. So recall that a general state vector psi can be written as a linear combination of the basis vectors. So in our spin 1/2 system, that essentially means A, some complex scalar, times the spin up ket plus B times the spin down ket. And we can rewrite that as in this way, where we just have that A can be replaced by the inner product of the spin up bra and the general state vector, and the B can be replaced by the spin down bra and the general state ket. Since those inner products are scalars, we can bring them to the other side of those basis kets, and then we can factor out that general state ket, and we're left with this, where we have the spin up ket with the spin up bra plus the spin down ket with the spin down bra, all operating on that general state vector. And that operator, that total operator in parentheses there, is what we call the identity operator. And it can be written as that spin up ket, spin down, spin up ket with the spin up bra plus the spin down ket with the spin down bra. Or in general, that was for our spin 1/2 system. For a general n-dimensional Hilbert space, that identity operator can be written as essentially what we're going to call the outer product of all the basis vectors spanning that Hilbert space. And this relationship is actually known as closure, or the completeness relationship. Completeness relation. And we've actually used this before. That essentially is how we know that that's the same way of writing a general vector can be written as a linear combination of our basis vectors. In matrix notation, you can sort of see how this operator is actually the identity operator. I mean, if we write out those ket bra combinations in their matrix representation, we get this, and carrying out that matrix algebra, we see that gives us our identity matrix, and we operate on any column vector with the identity matrix, we get back that column vector. So this notation does represent the identity operator in quantum mechanics. And again, I mentioned this briefly a second ago. This ket bra notation, or what we call the outer product, as opposed to the inner product when it's a bra ket sort of pairing. When it's a ket with a bra, we call that the outer product. And the individual outer products here are what we refer to as projection operators. So we have the projection, the spin up projection operator would be the spin up ket and the spin up bra. And in their matrix representation, it would be that, whereas the spin down projection operator would look like this. Now, why do we call these projection operators? Well, to get a handle on that, we're going to revisit our familiar position vectors we remember from introductory physics when we're trying to describe the position of some vector in our three-dimensional real space. We have our position vector is equal to, in Cartesian coordinates, the x component in the x hat direction plus y component in the y hat direction plus the z component in the z hat direction. And we can represent that as a column matrix of just the components of each of those directions. Right? Now, if we think about if we were trying to imagine what matrix or what operator would we act on that column vector to give us the projection of that vector in one of those directions, or basically how do we find out the magnitude of one of the components, we would simply take a matrix like this, and that would project our position column vector onto the x component, or in the x direction, and we would get a vector with that magnitude in the x direction. So that operator projects that position vector onto that component. This is analogous to what the projection operators are doing in our quantum mechanical Hilbert space. These outer products or projection operators are taking a general state vector and projecting it onto one of those basis vectors, or one of the vectors, whatever vector is forming that outer product or that projection operator. Now, this relates very closely with our concept of measurement in quantum mechanics. If you remember, postulate 4 says the probability of measuring a given outcome can be determined this way. So here we have, hopefully you can follow the notation here. I'm going to try and be as consistent as possible. This script P is referring to probabilities, not projection operators, which will be a different P. But the probability of measuring a spin up result in a Stern-Gerlach measurement was just this: the spin up bra acting on taking the inner product with the initial state vector. The magnitude of that squared gave us the probability of measuring that spin up result. We can expand that magnitude squared as essentially just the spin up, inner product of spin up and the general state, initial state prior to measurement, and the complex conjugate of that. Because we know that if you reverse the ket and the bra, you just get the complex conjugate of that, we can flip that second term there to get this. And since those are scalars, we can, they commute, so we can switch which order they're in to get this. And we see that probability can be written as just that projection in the spin up projection operator sandwiched between the system state ket and state bra. So we can rewrite that probability of obtaining a given measurement value, a given eigenvalue, using the projection operator for the eigenstate associated with that measurement outcome. That's not the only way it's related to measurement. It actually leads us to postulate 5. We know, and we saw this in those Stern-Gerlach experiments we used to sort of introduce all of this stuff, that the measurement of a physical observable, when we take that measurement, after the measurement, the state is now in the eigenstate that corresponds to whatever the result of that measurement was. So what that means is if we look at how the projection operator acts on a general state, we see that we get the state, it projects that ket onto the ket that corresponds to the eigenvalue we're talking about times some probability amplitude. So if we just normalize that ket by essentially dividing by the magnitude of that probability amplitude, which we can rewrite this way, if we normalize by dividing that ket, dividing by that magnitude, we get the ket that describes the system after the measurement. So that's essentially what postulate 5 is. After a measurement of some observable A that resulted in an eigenvalue A sub n, whatever the nth eigenvalue of that system is, the system will then be in a new state, call it psi prime, that is simply the normalized projection of the original system ket onto the eigenket or kets corresponding to the result of that measurement, which sounds pretty complicated, but is hopefully making a little more sense now that we understand what a projection operator is and what we mean by the normalized projection of that original system ket onto the eigenket. Essentially what it's saying is, if we go back to the Stern-Gerlach measurements, if we measure spin up state, we just take and we want to know what state the system is in now that we have made that measurement. It is just the projection operator onto that spin up, the projection operator of that measurement result, the spin up, operating on that initial state ket and normalize that. But in our spin 1/2 system, that's pretty straightforward. You end up you're in the spin up state like we expect. Anyway, this was a really brief lecture, just sort of introducing the concepts of the identity operator, the way we can write that using our bra-ket notation, as well as formally sort of introducing postulate 5 and understanding how that works. This gives us all the tools we need to analyze the last few Stern-Gerlach measurements we've discussed, which we're going to do in the next lecture, and go from there.